Hello, my name is Tom Sykes. I would like to talk to you today about an aspect of my PhD work from the University of Leeds that I have since moved to the University of Oxford as a postdoc working on a variety of droplet dynamics. In this very short talk, I will only give you a flavour of the multitude of interesting results we obtained during the course of this work, and at the end I'll direct you to a paper where you can find much more information if you would like to. In particular though, if you're interested in this work, then I invite you to contact me. So let's see how substrate wettability affects mixing during droplet coalescence. This work uses both high-speed imaging experiments and numerical simulations. As an initial condition, we have two droplets that are just touching and effectively static in axisymmetric configuration. Here, both free and sessile droplets have the same fluid properties, and in the experiments, the free droplet is dyed to make the internal flows visible. The droplets are millimetric with Onnesog number much less than 0.1, so the dynamics are dominated by surface tension. So if I play the first video, you can see that meniscus bridge is quickly formed between the two droplets and builds due to the excess surface energy that is inherent within the initial condition. The emitted capillary waves cause the coalesced droplet to stretch upwards and form a column, which subsequently crashes down towards the substrate. Once free surface oscillations die down, then you can see that the internal interface, which is made visible by the dye, is in fact flat. In the right-hand video that I'll play now, the only change is that the sessile droplet volume has been increased. Note that the sessile droplet volume is still smaller than the free droplet volume in this case, but the presence of the substrate causes the former's effective radius to be greater. Qualitatively, the external dynamics they look pretty similar between the two videos, but if you look carefully, you can see that only in the latter does an internal jet form. Since advective mixing requires both stretching and folding of fluid interfaces, we conclude that the case with the internal jet exhibits improved advective mixing. The key result from these experiments is that internal jets can form at surprisingly low droplet volume ratios in this droplet configuration compared to the well-studied case of two free droplets. This point is expanded upon somewhat within the paper. Now, let's think about the substrate wettability, which we can very easily vary numerically. In the numerical simulations within this work, we use a customized version of the interfoam solver in OpenFoam and the Kistler dynamic contact angle model with contact angle hysteresis. The simulations were meticulously quantitatively validated against our experiments, including the ones that I showed you on the previous slide. So the regime diagram that you can show here indicates the appearance or lack thereof of the internal jet, as you can see on the frames along the bottom. As indicated on the previous slide, larger sessile to free droplet volume ratios are conducive to internal jet formation. Moreover, the regime diagram shows that larger receding contact angles are also conducive to internal jet formation. In fact, every one of the 23 points that you can see on the diagram there has three simulations with different advancing contact angles. Only two of the points change classification for all three advancing contact angles, and you can see those in the top left of the regime diagram. For the largest contact angle of 120 degrees, a clear-cut jet is not seen for receding contact angles of 50 and 60 degrees on the top row. This is the only change throughout the whole regime diagram and confirms that the influence of the advancing contact angle is subordinated to that of the receding contact angle. Now, if we replot the data we have on the diagram here against contact angle hysteresis that has appeared on the right, we can see the importance of the receding contact angle. Unlike on the left, no clear regime boundaries can be seen in the right-hand regime map. To emphasize, the data included on both of these regime maps is identical, and the only difference is what's been plotted on the horizontal axis. Clearly, the receding contact angle is key, but why is that the case? So we can use the pressure distribution within the coalesced droplet to help us understand the influence of the receding contact angle we had identified on the previous slide, since the pressure distribution allows us to see capillary waves. I'll show you two videos from numerical simulations on this slide. The parameters between the two are identical, with the exception of the receding contact angle. A jet does not form in this case for a receding contact angle of 50 degrees, which is shown on the left, but a jet does form for a receding contact angle of 70 degrees, which is shown on the right. Within the coalesced droplet, both the pressure distribution is shown on the right-hand side. In the simulations, the pressure is initialized to be 0 everywhere, which is why you just see a constant grey colour there at the moment. So if I play the first video, then you can see the meniscus bridge builds, which causes capillary waves to be emitted, and they travel both up and down the free surface of the coalesced droplet. The initially downward traveling capillary waves hit the substrate and then are reflected away from it, back up the coalesced droplet. Whereas the capillary waves that initially travel upwards just act to stretch the droplet out and form the column that we previously discussed. So you can see at some point, the leading reflected capillary wave from the substrate, which is the local region of positive curvature, meets the region of negative curvature base of the column, as you can see on the stopped frame here. This interaction prevents negative curvature at the base of the column from dissipating, and therefore intensifies horizontal collapse of the neck that's formed. This horizontal collapse is the mechanism behind satellite formation. Here, though, no such satellite formation is seen, as the vertical collapse is sufficient to cause the column to merge into the bulk without further ado. Now let's look at the case with a higher receding contact angle. If I play this video, then you can see that the dynamics are similar initially, with capillary wave reflection leading to the interaction between the two regions of local positive and negative curvature again. However, due to the higher receding contact angle, the leading reflected capillary wave from the substrate is that much stronger that it intensifies horizontal collapse due to that negative curvature region. Not enough to create a satellite, but if I let the video continue on, you can see that it is enough for a tip with high curvature to form atop the coalesced droplet. The formation of this tip leads to a fast downward flow towards the substrate, which is what gives rise to the internal jet, sort of impinging jet, if you will. We found the presence of such a tip that you can see on the right here to be directly correlated with the appearance of a jet due to the rapid downward internal flow that it creates. The substrate wettability, principally via the receding contact angle, affects the ability to form such a tip as we've seen on this slide, and thus the ability to form an internal jet. Hence, substrate wettability affects advective mixing. As I mentioned before, you can find much more information about this work in a paper that we recently published in Langmuir. The paper is open access, and a link to it can be found in the video description. Thank you.